Hey guys, how's it going?
Good.
Pretty good.
Yes, I saw a few of you have taken the exam. How did you guys feel about it? How was the midterm? I think like 2/3 of you took it already.
I didn't think it was too bad, but I guess we'll see when I get my grades back.
Yeah, but it wasn't like I mean, time-wise, did you guys feel like you had enough time to do everything?
Definitely.
Yeah, okay, that's good. All right, so we'll finish the determinants today. Just to kind of recap what we did last time, right? So we went over the definition of determinants. We went over like different methods for computing determinants. So just to review a little bit. So for determinants, right, it's notation like determinant of a matrix A, or like if you want to write it shorter, sometimes it's easier just to put kind of this absolute value sort of sign over the matrix. That also means a determinant. And determinants are also only defined for square matrices, right? So it has to be an n by n matrix. So, and we did the definition that works for basically all sizes of matrices n by n, right? We can do our cofactor expansions along any row or any column, right? So I mean, we'll do more examples of this, right? But we can basically expand across any row. So we're taking elements in the row and multiplying them by cofactors. Right? And cofactors had like the plus or minus sign depending on like I plus j. And the other component of the cofactor is a determinant of the submatrix that were obtained by removing ith row in jth column. So for cofactor ij, you're basically looking at the determinant of a smaller matrix where you basically took your matrix A and removed ith row in jth column. All right, or you can do it about basically any column, right? So pick any row or any column. I mean, normally I want to pick something with the most amount of zeros, so it will be easier. And you can compute the determinant using this formula, right? So also we talked about if you have a triangular matrix, right? That was pretty simple proof, like you're just using your cofactor expansion, like about the first column or something. So the determinant of the triangular matrix, right, when all of the elements in this like lower triangular region are zero, is just going to be the product of your diagonal elements of the matrix. So triangular matrices are really easy to compute determinants of, right? And with this in mind, we also had another method for computing determinants. Is we can actually do our row reduction algorithm steps, right? With three operations, we can either add multiples of one row to another row of the matrix. Those operations don't change the value of the determinant. We can interchange rows of the matrix A, but in this case, every time you interchange rows, you're going to have to introduce a minus sign. And then the third operation, we can multiply a row by a matrix by any constant. Right, and maybe in this format was a little bit easier to use. So basically, if you have like one row where all of the entries are multiples of same number, you can basically factor that number out of the determinant. Right, so those three guys kind of give you another method for computing determinants where you can do your elementary row operation, adjusting the value of the determinant as needed. And once you have your row echelon form, your matrix would basically be a triangular matrix. So it would be easy to compute the determinant by just taking multiplication of all of the diagonal elements. So we'll do a little bit more examples of this. All right, but we'll basically have those two methods. And I mean, in practice, I mean, usually you can just kind of mix and match some of them. You can start with doing some elementary row operations. Once you get like a row column where mostly you have zeros, you can do your cofactor expansion, and then when you get smaller matrices, you can do more of this again. So we'll do an example like that one more time, right? So, and also we talked about our criteria for basically your matrix being invertible or not being invertible. And we use the fact that when we're doing those elementary row operations, how the value of the determinant changes. So multiplication by a constant is not really necessary for converting matrix A to your row echelon form. It's really only necessary to convert your matrix to reduced row echelon form, right? To get kind of ones on your diagonal. But kind of with those two guys, kind of adding multiples of one row to another row or interchanging rows, I mean, really the only thing that changes is just the plus or minus sign in front of your determinant. All right, so with that in mind, using our row reduction algorithm, I can basically take any n by n matrix A, and I can always convert it to a row echelon form. And in my row echelon form, I would always have a triangular matrix, but the only difference is that if A is invertible, all of the columns are going to be linearly independent. All right, so from our inverse matrix or invertible matrix theorem, right? So for invertible matrix, you're always going to have all of those non-zero elements on your diagonal. So you're going to have pivots in every row and every column. So when you compute the determinant of this row echelon form, it will really only differ from the determinant of A by the minus sign, right? Because I can just do row interchanges or row replacements, right? Row replacements don't change determinant, and row interchanges only can introduce that minus sign. Right, so the only difference between determinant of row echelon form and A is going to be plus or minus, right? So if my matrix is invertible, I have all my pivots that are not zero, so I'll be able to multiply all of those pivots together, and this will give me my determinant of U. And so determinant of A would just be plus or minus that determinant of U, right? So if I have all the pivots, my determinant is not going to be zero because I'm multiplying all of the non-zero numbers, right? So this kind of goes back and forward, right? So my matrix A is invertible, then determinant is not zero. And if determinant is not zero, then my matrix A is invertible. However, if my matrix is not invertible or singular, I mean, that means a lot of things by our theorem, right? My columns are not linearly independent, right? My linear operator defined by A is not onto, right? And things like that. And in terms of pivots, I mean, that just means I'm missing some pivots in some of the rows or columns, right? So kind of one example could be something like this, right? In this case, I have one row of all zeros. I'm missing pivot in the third column, so I have some free variables. But I mean, ultimately, this matrix U is row echelon form, and it's still diagonal. Well, it's still triangular, right? Because I have my triangular region of all zeros. But because I'm missing some pivots, when I start multiplying my diagonal entry, I'm going to have zeros in my multiplication. So determinant of U is going to be zero. And because determinant of A only differs by plus or minus sign, the determinant of A is going to be equal to zero. So we're kind of adding this another criteria for being able to tell if the inverse of the matrix exists. All right, so inverse exists if and only if determinant is not zero. But if determinant is zero, I mean, this is equivalent to having the case of missing some pivot. So inverse of A is not going to exist. All right, so kind of, I think like looking at those pictures and like thinking about the pivot all being present or some pivots being missing, kind of gives you a better idea about how those things are all related, right? Invertibility and value of the determinant and linear independence of columns and things like that, right? So we did this last time, and then the very, very last thing we did in the last lecture is we're going to summarize everything in one theorem, right? So square matrix is invertible if and only if the value of the determinant is not zero, all right? And again, we can relate it to all of those other things we did in the past, right? So we talked about null spaces, column spaces, right? If determinant is non-zero, then columns of A are linearly independent, right? Which means that A is invertible. And then, but also we can look a little bit at rows of A, because if determinant of A is not equal to zero, rows of A are also linearly independent. And I mean, you can relate that to A using the A transpose, right? So if I'm kind of switching rows and columns in my matrix, we already had the theorem that said that if A is invertible, then A transpose is invertible, and if A transpose is invertible, then A is invertible, all right? And kind of relating A transposes to determinants, we'll have a theorem in a little bit saying that actually determinant of A is going to be the same as determinant of A transpose, which conceptually makes sense because remember when we compute determinants, we can basically expand using cofactors about any row or any column, right? So kind of expanding about a row of A is pretty much the same as expanding about the column of A transpose. So our determinant of A and A transpose will be the same, right? But the main idea here is I can decide if my matrix is invertible or not just by looking at the value of the determinant of A. Right, so for invertibility, I need determinant not equal to 0. Right, so we can do a little bit more examples here, right? So if I have a matrix here, so I have 4 by 4, right? And I want to compute the determinant of it. So if I did the cofactor expansion, I mean, it's going to be a lot of work, right? I mean, I could pick the first row because it has 1, 0, but I still have, 1, and then I have to compute determinant of 3 by 3 minus 3, then another submatrix, 3 by 3, I have to compute determinant of. So I'm kind of lazy. Maybe I'll just try to make one of my columns mostly all zeros and just one entry, so then I only have to deal with one determinant of a 3 by 3. So I'm going to use that method where I know that the value of the determinant is not being affected if I start doing my elementary row operations when I'm adding multiples of one row to another row. So I'm basically going to eliminate this -2, 3, and 1, just like we do when we do row reduction, right? And I know the determinant of the resulting matrix is not going to change, right? So if I do eliminate -2, 3, 1, right? My resulting matrix is going to be this. Determinant is the same, so I'm basically computing determinant here. But at this step, what I can notice is my row 3 is exactly the same as row 4. So those two rows are linearly dependent, right? They're multiples. I mean, they're actually the same. They're not just multiples of each other, they're the same, right? So, and I know from the previous theorem that if my two rows of A are linearly dependent, then determinant will have to be equal to 0 and A is singular. So this is kind of like if and only if, right? They only have two options. They're linearly dependent or independent. Right? If determinant not 0, they're independent. If they're dependent, the determinant would have to be equal to 0, right? So in this case, if I notice that two of my rows are multiples of one another, I can immediately conclude that my determinant is equal to 0. So not just columns, but also rows, right? So I could do another example. So I want to compute the determinant of this matrix here. So also 4 by 4, right? And here you have to make a decision, right? Do I want to do cofactor expansion? Do I want to do a little bit of row reduction first? Or do I just want to do row reductions? I mean, in this case, I mean, it's always up to you, right? You can take different paths, right? As long as you're doing all the steps correctly. So, I mean, in this case, it looks like, well, if I took the first column here, I mean, I have 0, 0, and then I have two entries that are not 0, right? So maybe if I just do my row reduction step, just to get rid at least of one of them, so then I'll have all zeros and just one non-zero entry. And I mean, that's fine. I know that I can add multiples of one row to another row and not change the value of the determinant. So I'll do that here first. I have my determinant of this matrix A, right? And I'm going to just eliminate this -2, right? And I'm going to do it by basically adding row 2 to row 4. Right, so 2 minus 2 will be 0, right? And then I'm doing the same operation of the other entries. All right, so I did my elimination here, added one row to another row. I'm computing the determinant, so I know this operation does not change the value of the determinant. So now I have determinant of this new matrix, which is equivalent to this one. But now it's actually nice to do a cofactor expansion, right? I don't have to do one or the other method, I can mix them. Because I have a row of basically all zeros and just only one non-zero entry, I'll just switch to doing my cofactor expansion. I'll do cofactor expansion in the first column, because I only have one non-zero entry. And then with my cofactor expansion, remember you have to take care of the sign first and then compute your submatrix. So with the signs, you always have this checkerboard pattern. So plus, minus, so for this entry 2, the only non-zero one, I have to put my minus sign that comes from my cofactor, right? It's -1. I have second row, first column. So this is basically 2 plus 1, 3, -1 to the odd power gives me minus. And then my entry in my column 2. And then basically determinants of what is left when I remove second row, first column. So I have 1, 2, -1, 3, 6, 2, 0, -3, and 1. And so now I have a determinant of smaller matrix. I had 4 by 4, now I have 3 by 3. Right, and because I eliminated this -2, I only have to deal with one 3 by 3 determinant. So in this step, again, you have two options, right? You can either do cofactor expansion on this, or you can do some elimination steps, right? So maybe make more zeros in your columns or rows. And over here, I mean, I can work with the last row or the first column. So here I chose to work with the first column. I have 1, 3, and 0. So maybe I'll do my reduction here and I'll get rid of this 3, right? I know that if I add or subtract 3 times row 1 from row 2, value of determinant will not change, but I will have 0 here as a result. So I'm doing row 2 minus 3 row 1, eliminating this 3. And then I basically have a column with only one non-zero entry. And I can switch back to my cofactor expansion down the first column. Right, my signs are plus, minus, plus. So really the only term that survives is multiplied by this 1, so C11 cofactor. Right, so I have -2 times 1 because I applied plus sign. Then when I eliminate first row and first column, all I have left is 0, 5, -3, 1. Right, so that's a 2 by 2 determinant. And for those who know how to do this, right, you just take in your diagonals, plus and minus. So 0 times 1, -5 times -3. Right, so if you compute this, you're basically done. So you have like -2, right, times -5, -3, so plus 15, right, -2 times plus 15, or -30. So we got our determinant. That makes sense, guys? Right, so we have two methods for computing determinants here, either with cofactor expansions or doing our kind of step that we did for row reduction. Right, and you can kind of mix and match them, just depending on what matrix you have. For cofactor expansion, you really want to have a lot of zeros, right, to make your life a little bit easier. That makes sense? Questions on this? You guys all good with how to compute the determinants? And I mean, in real life, when you deal with matrices and like real life applications, you have really, really large matrices. You don't have like 3 by 3 or 4 by 4 or 5 by 5. You have like thousands or hundreds of thousands by hundreds of thousands. So you mostly do this stuff on a computer, but in order to do this on a computer, you need to write the algorithm how to do it. So you kind of figure out those algorithms on smaller matrices. You can do them by hand, but in practice, you kind of have to program it in on the computer, and the computer can do it for you. Right, but I mean, all of those kind of for hand calculations, cofactor expansion or row reduction are good methods to deal with determinants. All right, so let's do another theorem here. All right. So I mean, from theorems from previous chapters, we know that if A transpose is invertible, then the matrix A is invertible, and if A is invertible, then A transpose is invertible. So they're simultaneously invertible or simultaneously singular. Right? But in terms of determinants, we have a theorem which we'll prove here real quick. So again, we're dealing only with square matrices n by n. Then if I know determinant of A, I can immediately know determinant of A transpose because those guys will be equal, right? So determinant of A transpose equals to determinant of A. And remember, our A transpose is basically A where I'm turning my columns into rows, right? Or in other words, if my A has components ij, then my A transpose will have components ji. So I'm basically switching i's and j's, right? I'm switching rows and columns. Not so to prove this, I mean, we'll kind of run through the proof pretty quickly here. I mean, you have to use induction. You know, I don't know if you guys did. You guys done proofs by induction in other classes? I mean, the proof by induction basically relies on the fact that, you know, you have some statement that's true for n equals 1, maybe for n equals 2, or something like that. I mean, generally, you just take n equals 1. In some cases, you take n equals 1 and 2, right? So maybe you have a statement true for n equals 1 and 2, which is called your base case. Now, and then you want to show that the statement is true for all n. So what you do instead of kind of going over and proving it for all different n's, right? Because it's impossible if n could be arbitrarily large. What you do is you basically assume true for n equals to k, and then show that this implies true for n equals to k plus 1, right? So you're kind of assuming something is true for k, and then this would imply that it also is true for the next number, k plus 1, right? So you kind of have this stencil of true for k, then necessarily true for k plus 1. And you can reapply this stencil, and then if you know that something is true for n equals 1 or 2 or 3, right, then if it's true for 2, using the stencil, it would be true for 3. If it's true for 3, using the stencil, it's true for 4, it's true for 5, and so on. That's kind of the basic idea of proof by induction. And that's how you have to do this here, right? So you can look at your base cases, right? So I mean, I think you can pretty much just look at one, but I also did two. So 1 by 1 matrix is just a scalar, right? So my A is the same as A transpose. But for 2 by 2, right, my matrix A is A11, A12, A21, A22. But A transpose, I'm basically switching rows and columns, right? So my first row, A11, A12 becomes my first column, right? My second row becomes my second column, right? If I compute the determinant of A, I have A11 times A22 minus A12 times A21. If I compute the determinant of A transpose, I have A11, A22, right? My diagonal elements don't change when I transpose. But my off-diagonal elements basically just switch places, right? So instead of A12, A21, I have A21, A12. But multiplication for real numbers is commutative, so determinant of A equals to determinant of A transpose. Right? So we know for n equals 2, determinant of A equals to determinant of A transpose. And then what we'll do is do this induction step, the second step, right? I'm going to assume that this statement is true for all k by k matrices, and this must imply that it's also true for k plus 1 by k plus 1 matrices. Right? So just at least kind of, we'll run through it conceptually a little bit. All right, so we suppose that determinant of A equals to determinant A transpose for all k by k matrices. And we're going to let n be equal to k plus 1, so the next size up, right? So, and then we'll look at the cofactors, right? So the cofactor of A1J and A is C1J. Oh, I'll label it as A. And then the cofactor of AJ1 and A transpose, right? So I'm just switching my indices, is CJ1 A transpose, right? So I'm claiming that those two guys are equal, right? And we can kind of do this separately here on 3x3 matrix to kind of convince you guys in this statement. So if I just kind of don't, I mean, I can do it for 4x4, but just to understand it more conceptually. If I'm looking at matrix A, right, and I'm taking the first row in A is the same as first column in A transpose, right? So if this was like 3x3, my k plus 1 by k plus 1 case, then when I start doing my cofactor expansion, when I compute determinant of A along the first row, I have, right, my A11, A12, A13 multiplied by cofactors, right? And if I was doing the cofactor expansion of A transpose along the first column, right? So I'm taking the same elements basically, because rows are columns now, and multiplying by cofactors in A transpose. So those two determinants will be equal provided my cofactors are the same, right? But if I look at my cofactors, okay, cofactor of A11 is what's left when I remove first row, first column, right? 2, 2, 2, 3, A32, A33, right? In A transpose, cofactor of A11 is going to be what's left when I remove first row and first column, and it's this matrix here, 2, 2, 3, 2, 2, 3, 3, 3, right? 2, 2, 3, 2, 2, 3, 3, 3, right? But those are five smaller matrix determinants. And if you look at them, you can notice that diagonal elements are the same, and off diagonal elements just switch places, right? 2, 3, 3, 2, 2, 3, 3, 2, right? So those two guys are just transposes of one another. And we know that for one size smaller matrices transposes, determinant of this is going to be equal to determinant of that, right? So because my cofactors involve determinants of one size smaller matrices, which I assume determinants are equal for A and A transpose, so all of those guys will be equal, right? And I mean, you can see it on this example of 3x3, right? If you compute all of your cofactors, I mean, you have the same diagonal elements, you have different off-diagonal elements. I mean, this minus sign comes from my sign pattern, like plus, minus, plus, plus, minus, plus, all right? But they are going to be equal because my basically submatrices in my cofactors are going to be transposes of one another, all right? Those transposes will be equal. So you can show that determinant of A equals the determinant of A transpose in this case. Does that make sense? Yeah. So I mean, I mean, I'm not gonna ask you to do too many proofs for this class, but I think it kind of helps a little bit to understand this. I mean, like the basic idea of why those two guys are equal is because when I do determinant, I can expand along any row or any column. So if I'm expanding around the row of A, that's equivalent to expanding around the column in A transpose. So determinants are equal here. Any questions? All right. So the last thing for this chapter. So very important property of determinants, and also something very important to be careful about. So for determinants, if I have two matrices, square matrices, the provided multiplication is defined. The determinant of the product of two matrices is the same as the product of the determinant. So determinant of A times B is the same as determinant A times determinant B. So very nice and important property that, I mean, sometimes may even help you compute determinants. Sometimes it may be easier to compute them separately, or sometimes it's easier to maybe compute the determinant of the product, because then you're computing just one determinant versus computing two determinants. rather than multiplying them. All right, so going kind of both ways could be useful for this. And then we can check this, right? If I have two matrices A and B, if I compute the product of A and B, I have another 2 by 2 matrix. And if I compute determinant of the product, I get 45. And if I compute determinants of A and B individually and multiply them, it's the same number. But we will prove this theorem in a little bit. All right, so I mean, this always holds, provided multiplication is defined, right? Both our matrices are square and like they have the same n, right? 2 by 2, 2 by 2, or 3 by 3, 3 by 3, and so on. But you have to be careful because, you know, if you kind of just memorize this property, sometimes people make mistakes because you can quickly assume that maybe determinant of the sum also equals to the sum of the determinants, and in general, it's not true, right? So, I mean, we can even use this example to show that it doesn't work even just for this example, right? If I add A and B and compute the determinant of the sum, I get 24, but if I compute the determinant of A and B and sum this up, it's 14, so not 24. All right, so this rule basically only works for multiplication of matrices, but not for addition. So be careful with addition. I mean, it's a very, very common mistake people make with determinants. But we can prove this property here. And I mean, the proof basically relies on your elementary matrices. Remember, the elementary matrices perform elementary row operations, right? Well, for one, if A is singular, then determinant of A is 0. And we showed earlier that if A is singular, then singular matrix multiplied by any other matrix is still going to be singular. Right, well, you also kind of did this with elementary matrices. But if A is invertible, we know that A is row equivalent to IN, right? Remember when we were doing, when we were finding inverses, we were starting with like A and I joined together and basically doing elementary row operations on A until it became I, and then I becomes A inverse. So A is row equivalent to I. I can do elementary row operations to convert A to identity matrix. And each one of those elementary row operations I can describe as an elementary matrix, right? So each one of those is performed like which is row, that's multiple of one row to another row, multiplies the row by a constant. All right, so I can basically express each one of those elementary row operations as multiplication by those elementary matrices. And so my A is basically multiplication of those matrices times the identity matrix I. So now if I start with my determinant of the product, determinant A times B, so I'm computing determinant A times B. What I can do, I can just write down my A as this multiplication of elementary matrices times I, and I'm not writing I because it's just basically equivalent of 1 times B, right? So instead of A, I'm just writing its representation of this multiplication of elementary matrices, right? So, and each time you perform an elementary row operation, right? Remember when I'm doing determinants, so this very last elementary row operation, I did EP, right? So whatever I did here, it did one of the three things. Either it did not change determinant, introduced the minus sign, or introduced some scalar multiplication. But remember, when we constructed those elementary matrices, to construct an elementary matrix, you basically take an identity and perform exactly the same elementary row operation on it. So I can basically factor it out as its own determinant multiplied by everything else, because whatever this did say, this multiplied a row by some constant, then the action of this EP is just multiplication by K. But if I factor this out, the determinant of EP is also just K. So I'm kind of multiplying it by everything else here and multiplying everything that's left except for EP by K is the same thing. So I can basically take each one of those guys one at a time and factor them out in separate determinants. So it kind of like looks like I'm just using the same property that I'm trying to prove, but I can't immediately just split apart A and B. But what I can't split apart is my elementary matrix determinants. So I can kind of factor all of them out and it's individual determinants. Right, so I basically have multiplication of all of those determinants of elementary matrices times B. And then I can regroup them back together. So I can put all of those guys in one determinant multiplied by determinant of B, right? But remember, all of this multiplication is just my matrix A. So then I can rewrite this as A. And that gives me determinant A equals to determinant B. Does that make sense? So again, the idea here is that I can't immediately split the determinant A and determinant B from this multiplication inside the determinant AB, but because A can be factored into those elementary matrices, those guys I can split away into separate determinants, right? And then when I regroup them back together, that gives me the determinant of A here. But again, it doesn't work for addition because with addition, I definitely can't use this fact here. Make sense? Any questions so far? So again, I mean, I'm not going to ask you to prove those things, but you definitely need to remember those properties, know how to use them. All right. So we'll do a little bit of applications and more properties of determinants here. And we'll start with what's called Kramer's rule. I'm not sure. I think you should have done a little bit of this in just college algebra. You guys had time in my class, right? So Kramer's rule is another way for solving linear systems. I mean, in general, it's not very efficient method for hand calculations unless you have like really small, like 2x2 or 3x3 matrices. But it's very useful for like some theoretical applications or for cases when you're trying to find solutions to linear systems that may depend on some other variables. So maybe your X depends on some other parameter, and you want to find the general formula for X in terms of that parameter. So we'll do some examples like this. But I mean, it's basically another way for finding solutions for a linear system, right? And of course, we know that the system will have a unique solution if A is invertible. So for an invertible matrix A, we can take any B in Rn and have a unique solution X, right? We showed that before because when you have AX equals to B, if I just multiply everything by inverse, A inverse B, I basically get my unique solution A equals to X equals to A inverse times B, right? Provided inverse exists. But this method gives me basically the formula for my solution. So each xi component of my x, right, x1, x2, all the way to xn, it gives me formula for each one of the components of the solution vector. And it's defined as determinant of ai of b divided by determinant of a. And what is my ai of b? ai of b is basically my matrix A, where I'm taking the ith column and inserting my vector B instead of the ith column in A. All right, so it gives me kind of nice and easy to remember formula for computing x's, but we'll have to dig into it a little bit and with the proof, right? Because I mean, it's not really intuitive immediately, right? Why this is true. Because before what we did to find solutions were like row reduction or kind of using matrix inverses. I mean, here it looks very different, right? So why is this true? We'll kind of go like step by step here. So if I start with matrix A, right? Matrix A has columns and columns labeled A1 through AN. If I have matrix identity matrix, I can also look at it in terms of columns, right? Identity matrix has my unit basis vectors as columns. So if I have identity matrix I of X, right, so it's just kind of like in this definition here, my subscript I means that I'm basically taking my matrix A and replacing I column with B. Here I'm taking my identity matrix and replacing I column of identity matrix with the vector X. All right, so all of my columns are the same as identity and X's for column I. Right, so for like 3x3 case, my example is I had identity and just the third column here I replaced with X. This is I3 of X in the 4x4 case. So that's what my identity I of X is. So then if I look at when I'm multiplying matrix A by identity I of X, so this guy here, I'm going to have A multiplied by all of those columns. By definition of matrix multiplication, when I'm multiplying a matrix by columns of the other matrix, I can just basically take this A inside, right? So it's A times the first column, A times second, matrix A multiplied by all of the columns generates the columns of the new matrix that I have from this multiplication, right? And in this case, we know that if I multiply matrix A by those unit basis vectors, right, A times E1 is going to be just the first column of A, right? Whenever I'm multiplying matrix A by EJ, I'm basically getting my jth column of A, right? My EJ is just 0, 0, 1 in the jth position, 0, 0. Basically just isolates the jth column of my matrix, right? So basically this A times identity I of X is the same as AI of B, right? Because I have all columns the same as A, and then this column where I replaced I column with X, I have A multiplied to X, which I know is B from my equation. So this equals to that, right? And this is the equation we're going to use to basically show our theorem here, right? So I'll rewrite this over here, right? And then I'm going to use determinants, right? Because I have determinants in my formula. So if I take determinant of both sides of this, here I'm taking determinant of multiplication of two matrices, right? Determinant of A times identity IX. And over here, I'm just taking determinant of my matrix A with B for column I. Because here is multiplication, I know from the previous theorem that determinant of the product is product of the determinants. So here I will have determinant A multiplied by determinant of my identity matrix with column I replaced by X, right? And I basically have most of the components of my formula here, right? Determinant AI B divided by determinant A. Right, I have determinant A, which is not 0, right? Because I'm looking for systems that have unique solutions. Determinant AI of B. So if I divide by determinant A, all I have left to do is show that determinant of this identity matrix with I column replaced by X is actually just my I component of the vector X, right? And that would give me my Cramer's rule formula. So, and for this, I wrote out once you see kind of the matrix, it makes a lot more sense, right? So what is my identity matrix with column I replaced by X, right? So if I kind of draw the general matrix, this is my I column, right? Everything else is like an identity matrix. So if I compute the determinant of this, I'm going to choose I row, not I column, but I row. Because in I row, the only thing I have that's non-zero is this component xi, right? So if I do my cofactor expansion, I mean, this xi is located in I row and I column, right? And it's the only non-zero entry. So if I do my cofactor expansion, I have -1 to the power I plus I throw ith column. So I plus I is 2i, which is even number, so this will be plus. Now, then I have the element in my row, xi, multiplied by everything that's left when I remove ith row and ith column. And if you remove ith row and ith column, right, your matrix basically becomes smaller, but it's still going to be an identity matrix, right? Just think of it, you're deleting it. So, I mean, this hole here that didn't have one, now those two ones move next to one another, and it's still going to be an identity matrix, but one size smaller, right? So if this I was like 4 by 4, this one will be 3 by 3. Right? So this would be true for any n by n matrix with any column I replaced by x, right? Because I will always have I plus I, so this minus will always be a plus, and I always have xi, and I always have some sort of identity matrix here. So all of this just collapses to being equal to xi. That makes sense? Right. So and this basically proves our Cramer's rule, right? So I can basically compute my solution for the system by computing individually components of this vector by taking determinants of my matrix A with ith column replaced by B and dividing by determinant of A. So it's, I mean, it's pretty straightforward rule to kind of apply to solve systems, but again, for larger matrices, but you have to compute a lot of determinants here, right? For each element x, you have to compute the determinant of a matrix with like B being in different columns, right? So it's for n by n system, you basically have to compute n plus 1 determinants, right? And determinants sometimes could be pretty lengthy to compute, which is why it's not very efficient for like hand calculations, unless you really have to get some formula for something. All right, but we can do this for like 2 by 2 case or 3 by 3 case. I mean, it's not really that much longer or not longer at all than doing other methods. All right, so and for example, for 2 by 2 case, if I'm trying to solve this system here, all right, 3x1 minus 2x2 equals 6 and other equation. I mean, I can just, you know, pull out all of the coefficients from my matrix A, right? If I want to rewrite this in the matrix form, right, I'm going to have 3 minus 5 minus 2, 4, my matrix A multiplied by my known vector x1, x2 equals to my vector B, which is 6 and 8. We're kind of converting from system form to matrix equation form. So I have my matrix A. So constructing my A1 and A2 of B, I'm just looking at my matrix A for A1. I'm taking vector B and putting it in the first column. All right, so my vector B and put it in the first column of A. And for my A2, I'm taking my vector B and replacing second column of A with my B. That's all I have to do. Then you have to do your determinants, right? If you do determinant of A, this will be not zero, so good, my system will have a unique solution. And then you also have to compute determinants of those two guys, right? So, but I mean, those are 2 by 2 matrices, so it's not difficult, right? 6 times 4 minus 2 times 8, 3 times 8 minus 6 times minus 5. Right, so I computed those three guys. And then using my Cramer's rule, right, it's just the formula, x1, determinant A1 of B divided by determinant A, so 40 over 2 close to 20. And x2 is determinant of A2 of B divided by determinant A, right? So I have this 54 divided by 2, right, is 27. So, I mean, that's nice. I'm getting the nice solution for my system. But again, for 2 by 2 keys, I mean, it's not really shorter than doing it by row reduction or by finding an inverse matrix or by, I mean, you can even do simple like substitution, right, to compute. So just, you know, depending what you prefer to do. Like if you like doing determinants, you can do it with determinants. Does that make sense? Probably more useful application of this. Your book had an example, which I think was pretty good. So if you guys doing any like electrical engineering or control systems engineering, like, I mean, and then, I mean, a lot of applications of this. I mean, you probably see it first when you do differential equations. When you do what's called Laplace transform, you kind of like converting problems, like you can have a problem that you're solving for the time variable, but you can convert it to a frequency variable f, which is when you do Laplace transform. But I mean, it's not really that important for us here, but it's kind of a good example of when this method of Cramer's rule is kind of useful for finding solutions, because it really gives you a nice formula in terms of some parameters that you may not know immediately. You get a formula for your solution, which should be harder to do with just like row reduction. So in this case, say if I have a system, right, and I don't just have variables x1 and x2, which I need to solve for, I have a parameter s here, which may vary, right? So maybe I don't know it initially, but I want to solve the system with f in it so that I can later plug it in and figure out what the value is. All right, so my matrix A will have parameter s in it. It will be, in this case, doesn't, but you know, it could also have parameters. But I'm going the same way, right? My s is just some constant, which I just don't know yet, right? And then I copy down all of my coefficients of x1 and x2 into my matrix A. I construct my A1 and A2 by basically taking my B and replacing first column with B and replacing second column with B, right? And then I can just use my formula again for Cramer's rule. So if I do determinant of A, I mean, it doesn't matter that I don't know S, I can just express that in terms of S, right? So my determinant of A is, right, 3s squared minus 2 times minus 6, right? So 3s squared minus 12, right? I factor out 3. And then since I don't know S, and in order to be able to determine if I have a unique solution, I need to have determinant not 0, right? So here I know that, well, I definitely don't want to use s's when s equals to plus or minus 2, because if s is 2, this is 0. If s is minus 2, this is 0. So for determinants to not be equal to 0, I need s to not be equal to plus or minus 2 to have a unique solution. And then provided s is not plus or minus 2, you know, I'm just applying formula, right? I'm taking determinant of A1, 4 times s minus 2 times 1, right? So it gives me 4s plus 2 divided by determinant A. And then I have my x2, determinant of A2, 3s times 1 minus 4 times minus 6, right? Also in terms of s, right? Divided by determinant of A. So in this case, I'm getting my solution x basically in terms of this parameter s. And then later on, once I know what my s is, I would be able to kind of write everything down without having to solve the system again, right? If I was using row reduction, I would have to kind of solve the system this long way every time I have a different s, right? But over here, I have a formula in terms of s. So if I want to compute solutions for all kinds of different values of s, I don't have to solve my system every time because I already have a formula for my solution. For x, I can say like x is a function of s or something. That makes sense? Yeah. I mean, when you do inverses, it also kind of helps, except it's harder to compute inverse when you have variables present in it, right? Because if you're doing row reduction to find an inverse, you also kind of need to have numbers that you already know, right? But this method gives you a good way for kind of generating formulas for solution in terms of some unknown parameters. That makes sense? Question so far? No? All right, so another thing. Also got a lot of different applications and extra formulas. So we can also derive a formula for the inverse of the matrix, provided the matrix is invertible, right? And again, this is not a good method for hand computations. If you have a matrix A and you want to find an inverse of A, this is a very long way to do this. But for some theoretical applications, like this, it's good to have a formula. Like if you want to have a formula in terms of some general values, right, which you might not know immediately. Like this would be a good way to do this, but it is much longer than doing it by row reduction. All right, but it's nice to have a formula, and here our formula is defined as A inverse is given by 1 over determinant of A. And remember, determinant has to be not 0 for inverse to exist, so everything is defined here. Multiplied by this new matrix, which we're going to call adjoint of A or adjugate of A. And this new matrix is basically constructed by taking each element in A, computing its cofactor, and then taking a transpose of that matrix. Right, so the adjoint of A is basically a matrix of cofactors of A, where I'm switching rows with columns. And so kind of be careful with this formula, because when you look at it immediately, it just looks like adjoint of A is cofactors of A, but it's actually a transpose, right? Because I have C11, C12, I mean C12 should be an element that's in the first row, not in the second row. All right. So then, like, how do we get to this? And we're actually using our Cramer's rule to get this formula. So we did Cramer's rule earlier. So we're gonna go to another application of Cramer's rule for deriving formulas for maybe some other things in linear algebra. Now, so, but to prove this, it's not too hard, but I mean, kind of helps looking at matrices a little bit. So, I mean, it looks like in order to get this formula, what we did is we tried to express each one of the components of A inverse, right? What were my components of A inverse? So if I define vector X to be J's column of A inverse, right? So basically looking, okay, if I want formula for A inverse, what are all of the components, like A11 inverse, A12 inverse, right, so on, A1n inverse, A21 inverse, A22 inverse, all the way to AN1 inverse, and so on. And so I'm trying to get the formula. I'm trying to see, well, I mean, what is the general formula for like Aij inverse, the ijth component of A inverse? Right, and what you do is first you look at the, what is my ith column of, what is my jth column of A inverse, and then you look at the individual entries of that jth column. Right, so that's what I'm doing here. I'm looking at the jth column of A inverse. I'm going to write it as X. And I know to get the jth column of any matrix, all I have to do is just multiply it by EJ, right? My unit basis vector with everything 0 except for the jth component. All right, so A inverse times EJ is exactly the jth column of A inverse, right? Which I will write as X1, X2, Xi, all the way to Xn. So kind of like, well, I guess that would be the next step here. Does that make sense? Taking the jth column. All right, and in the jth column, I'll just relabel everything as like X1, X2. Right, this is going to be Xi, Xn. Jth column of A inverse is X. Not expressed as this. So now if I multiply both sides of this by A, I will have AX equals to A times A inverse, which is I, is EJ. So I basically have another representation for this that's a little bit less intuitive than just basically taking J's column of A inverse. I have AX equals to EJ, right? The matrix, I'm inverting it. So A multiplied by J column of A inverse is EJ, right? So then by Kramer's rule, what do I know? I know when I'm solving this equation, because this is basically the same as solving equation AX equals to B, where my B is EJ. By Kramer's rule, each one of the components of X, right, is going to be determinant of matrix A with I row replaced by B, which is now EJ. So I'm applying Kramer's rule here to get Xi, which is determinant of A with I column replaced by J divided by determinant A. So I'm just applying my Kramer's rule right here to solve this system. But remember, my Xi is ij's entry in A inverse, right? Because it's ith entry in the jth column, right? So this ij's entry in A inverse over here, my Xi. So, all right, and I mean, now what I need to do, remember, I'm trying to prove this formula here. So I have determinant of A here, so I have that part. So now all I have to basically do is show that determinant of AI of EJ is exactly the formula for generating the adjoint of my matrix. Right, so I'm going to look at determinant of matrix A with I column replaced by EJ. I can rewrite this for kind of general invariant matrix. So I'm taking my matrix A. I have I column, and instead of I column, I'm writing down my unit basis vector J, right? So that one is all zeros except for one, which comes in a jth row, right? So what is the determinant of this matrix here? Well, do your cofactor expansion and choose the row column that has the most zeros. So obviously this one is the best one, right? Where I have my EJ, everything is zero except for one, right? So when I do cofactor expansion down I column, really the only entry that I'll have to work with is this entry in the jth row, one, right? So for my cofactor expansion, okay, I'm going to have -1 to the power j plus I multiplied by 1 multiplied by determinant of what's left when I remove jth row and ith column, right? Which really is exactly my CJI, right? Jth row, ith column, CJI. And this is where the transpose property comes from, right? It's not Cij, it's Cji, because I had my ith column and jth row because I had EJ, right? So this becomes Ji, determinant of AJi, and this gives me my cofactor Ji. All right, so if you go back to your formula for your Xi, my Xi was determinant of AI of EJ, right, divided by determinant A. Right. And this is my CJI. So I have 1 over determinant of A times my cofactor CJI. And I can populate basically my matrix A inverse with all of those guys, which is exactly what gives me my formula here, right, for adjoint of A. Does that make sense? Yeah? Any questions so far? All right. Yeah, but again, the formula is good for theoretical purposes. If you were trying to apply the formula, like to compute inverses, like you can see in this example, it's going to be pretty long, right? Because if I start using formula, I need to compute my adjoint matrix. And adjoint matrix consists of my cofactors for each entry. So if I have a 3x3 matrix, I basically have to compute 9 different cofactors. I have to compute 9 determinants of 2x2 matrices. So it becomes pretty long, right? So if I compute my adjoint here, I mean, I'll do this once, right? I'm taking all of my entries in A, right? The C11 with plus sign will be determinant of -1, 1, 4, -2, right? My C21, I have 1 with the minus sign, right? And what's left when I remove second row and first column, 1, 3, 4, -2, right? And so on. So you basically compute cofactors of all entries in matrix A. And then you have to put it into your formula for the adjoint, right? Except you have to remember that is going to be a transpose, right? So this 3 is going to be my C, not C21, but C12. And this is my C13. This 14 is my C21, and this is my C31. That makes sense? So again, but for hand calculations, this is very long. And we're not really exactly done yet, right? Because our formula for A inverse is 1 over determinant of A multiplied by adjoint of A. So I know adjoint. Now I also have to compute the determinant of the matrix A. All right, so I can do this here and by some cofactor expansion. So determinant is 14. And then I can put everything together to get the formula for A inverse. So again, if you're just doing it for calculation, I mean, this is long, but if your matrix A has some variable or some unknown parameters in it, this actually gives you a nice strategy for getting the formula for A inverse in terms of some unknown parameters. You can't really do that with doing row elimination algorithm, right? Because you really need to have some fixed numbers to be able to do your elimination steps. But here you have a way to find like an explicit formula for A inverse. Right there. My theorem here. So good for finding explicit formula in terms of unknown parameters. Just like in the previous example with S. So if I wanted to find, like if my matrix A has some variables in it, I would still be able to find an inverse. That makes sense? All right. So, but I mean, this was way one as well. There's also another way to do this. Once, if I have found the adjoint first, I didn't find the determinant of A yet. So one other way to do this would be if I know the adjoint of A and I know A, I also know that this formula holds, right? A inverse is 1 over determinant times the adjoint. And one thing you can do, I can multiply both sides of the formula by determinant A times A. Like on the right or on the left, it doesn't really matter in this case, right? So if I multiply A inverse by determinant A times A and A inverse becomes I. So I have determinant A multiplied by I. And on the right-hand side, the determinant of A is just a number, so I can cancel it out. And then all I have left is A multiplied by the adjoint. So, another way to find the determinant of A using the formula would be not doing the cofactor expansion, but using the formula and actually using the fact that determinant A times I would be equal to A times the adjoint. So I can just multiply those two matrices together. If I do this, I'll see that I basically end up having the same number in the diagonal and everything else is 0, which is basically my determinant of A multiplied by I. So in this case, I basically didn't have to compute determinant of A explicitly. I used the formula for A inverse to compute the determinant of A, and then I'm plugging in that determinant back into the formula for A inverse. Does that make sense? But I mean, one or the other way, I'm just gonna have two options. Like if you really don't want to compute the determinant of A, and if you would rather do multiplication of matrices than doing a cofactor expansion to find the determinant of A, you can do it this way. Make sense? All right, so let's do this formula. We're, well, not sort of done, but all the formulas for things that only relate to determinants and systems. And we also have some applications. Again, maybe you guys have seen this before. If you do it in algebra or trigonometry, you kind of prove this in a slightly different way with just angles and like trigonometric functions. But all right, here we have basically one formula for if I have a parallelogram that is defined by some two vectors that I can always express as columns of some matrix A. All right, so say in 2 dimensions, x1, x2, I have two vectors, a1 and a2, that are columns of some matrix A, right? I mean, they could be linearly dependent, but for linearly dependent case, determinant is going to be 0, and that gives me 0 area, right? Linearly dependent vectors would be pointing in the same direction, so the area is 0. So it's not very interesting case. So we're kind of assuming that A1 and A2 are linearly independent so that those two vectors actually generate a parallelogram with non-zero area. Right? So, and the theorem tells us that I can compute the area of the parallelogram defined by those two vectors by basically just looking at the value of the determinant and taking an absolute value of it. So determinant could be positive or negative, but for area, you just take absolute value and then take the positive value for the determinant. So why is this true? I mean, for a very simple case, like if I had a square is also a parallelogram, right? The square would be defined by basically columns of the diagonal matrix, right? If I take A1 with components A0, and I take A2 with component 0B, right? So this defines two sides of my square, side with length A and side with length B. Now, if I put those two vectors as columns in my matrix A, this is A0, 0B, so diagonal matrix. And then the area will be equal to the determinant of the diagonal matrix, which is multiplication of diagonal elements, A times B, right? Which makes sense, right? The area is base times height in this case, so this is correct. But does this work for the more general case, right? Because maybe my vectors don't have to be oriented at the right angle. It's parallelogram, right? This could be any angle. Right? So if I take any two vectors, A1 and A2, put them as the columns in my matrix, take the determinant of this, take absolute value, would that always give me the area of the parallelogram? Why is that true? Right, so if you have seen this before, you probably did this more kind of geometrically. It's like looking at like different like sides here, but I mean, we can actually do this in terms of the vectors also, and in terms of like properties of determinants and properties of matrices and converting matrices to diagonal matrices. So we'll kind of, again, look at it conceptually here just to kind of get an idea of why this is true, right? So we know it's true for simple case when matrix A is diagonal. For general case, my matrix A is probably not diagonal, right? So I will have some components, right? A11, A12, A21, A22. Now, but when we were doing our elementary row operations, right? Remember, I can do elementary row operations on this to try and convert it to like row echelon form or reduced row echelon form, right? So if the columns of my matrix are linearly independent, my matrix A is invertible. So I will have pivots in every row and in every column. So I can do elementary row operations to convert this matrix to a matrix that is diagonal, right? And if I do that, what happens to my determinant? Well, if I stay away from multiplying rows by some non-zero constant and only stick to adding multiples of one row to another row or interchanging rows, then the only thing that happens to my determinant is that I may have plus or minus sign changes. But I'm taking the absolute value here, so nothing will change about the absolute value of the determinant. Right, if I do elementary row operations on this general matrix to convert it to a diagonal matrix, which would be similar to this simple case, the absolute value of the determinant will not change, right? So the only other thing we would need to show is that the other side of the equation, that the area is not going to change when I'm doing those elementary row operations. All right, and you can sort of do this geometrically. So again, I'm not gonna ask you to prove things like this, but it kind of helps understanding, why this works, and also helps maybe remembering the theorems a little bit better. So for showing that the area will not change, right, you can kind of think of the simple general case, right? If I have vector A1 and A2 and they define this parallelogram, right? So what I want to do is I want to show that I can basically transform this parallelogram into what looks like a square, right? Because the square is basically just the rotation of this square region here, which I already know the determinant of diagonal matrix will give me the correct area, right? So can we deform this with just elementary row column operations? And yes, we can, because one thing to look at is area of parallelogram is base times height, right? So if I look at one of my vectors, the A1 as the base, right? Then normally my height is going to be this value here, right, at the right angle to the base. My A2 is not parallel to height in general, but otherwise it would just be a simple case of parallelogram where parallelogram is like a rectangle. Right? But what do I need to do to my A2 to kind of move it to H and keep the area the same? Right, and it's not that difficult if you just kind of like take this and rotate it, right, so that you have horizontal direction is the span of the vector A1, right? It's a little bit easier to see when you rotate it. Right, so let's say horizontal is span of A1. Right, so I'm kind of rotating this direction for this picture. Right, this is my A1, this is my A2, this is my height of the parallelogram. So the area of this parallelogram defined by A1 and A2 is H times B, base times height. Right. So what if I take the span of A1 and add A2 to it, right? This will basically be kind of a shift in this line up by A2, right? So I'm moving all of the points in span of A1 up by a vector A2, right? And then in order to generate a square, if I take a point over here, I mean, I will have some value C, right? So that I can take my A2, add C times A1 by parallelogram rule, and this would be my new vector here. So for, I mean, A scalar C, the area of the parallelogram defined by A1 and A2, so this parallelogram here, I can basically redefine an area of the parallelogram defined by A1 here base and height given by A2 plus BA1. And so basically this one here. So those two parallelograms have the same base and the same height, so they have the same area. And while this one is a little bit harder to deal with in terms of matrices because it's not a triangular matrix, I mean, this one is easier because, I mean, it's basically a square, right? And at the same time, I'm not changing the value of the determinant because all I'm doing here is I'm adding a multiple of one column to another column, which does not change the value of the determinant. And does that make sense? So, I mean, we didn't do it too rigorously, but at least conceptually, I think it's good to, I mean, see why this formula holds for any two vectors in R2 to get the area. That makes sense, guys? I mean, just let's do one quick example before we stop. So also be careful with this when you're computing your areas, right? Because when I'm working with determinants and vectors defining parallelogram, my vectors start at the origin, right? I'm assuming that my A1 is basically a coordinate of this point here, right? So I'm assuming that my vectors kind of originate at the origin and go to the corresponding point. And so if I have, say, a problem of, like, I want to calculate the area of the parallelogram defined by those 4 points, right? If I draw the 4 points, yeah, I have a parallelogram, but if I want to use the determinants to find the area of this, I need to find those two vectors that define this parallelogram. And in this case, it's a little bit harder because, you know, I don't really have anything. I don't have a vertex at the origin. So I really need to have a vertex at the origin. But it's not too bad here because I can just move everything a little bit in order to, I'm going to move this vertex -2 to the origin. And so, I mean, if I just take this parallelogram and shift it, I'm not changing the area, right? I'm doing a rigid transformation. And all you have to do is just basically shift each one of the points by 2 units to the right and 2 units up, right? So my -2 will become 0, 0. This is vertex. Then 0 and 3, I'm just adding 2 to everything, become 2 and 5, 4, 5, 6, -1 plus 2, 1, 6 plus 2, 8, 4 plus 2, 6. So I'm just moving all of my vertices by 2 units up and by 2 units down. And now, since my one vertex is at the origin, I can basically define my 2 vectors at A1, 2 and 5, and A2, 6 and 1. And use my definition with the determinant, right? If I want to find the area of this parallelogram is going to be the determinant of the matrix A formed by using those 2 vectors as columns. So 2, 5, first column, 6, 1, second column. I take the determinant, it equals to -28. But that's okay because my area is absolute value of the determinant, right? So area will be 28. That makes sense? So if you didn't do this step here and just started looking at kind of the point, then you'd make mistakes, right? Because if you took this as a vector and this as a vector, like, then this is not really the area of the parallelogram that you want. So you really need to have one vertex at the origin, and then you can take the other 2 vertices as your vectors defining size of parallelogram. That makes sense, guys? Not too bad. So maybe just one last thing so we don't, I mean, you can also basically apply this for, not really for any number of dimensions, but let's understand conceptually, maybe just for 3 by 3 matrices. I mean, the same concept of doing the determinant, if A is a 3 by 3 matrix, then maybe A consists of 3 columns, which are vectors in R3, right? And if you take the absolute value of the determinant of this matrix A, you're not getting the area of the parallelogram, you're actually getting the volume of the parallelepiped defined by those three columns of the matrix A. Right? And again, you can kind of do this by simple case, right? So if my matrix A was diagonal, then I'm basically getting, right, first vector is A0, 0 along x1, 0b0 along x2, and 0, 0, c along x3, right? So I have my parallelepiped, and the volume of the parallelepiped is, right, area of the base multiplied by height c, so A, B, C. And then determinant of the triangular matrix is multiplication of diagonal elements, right? So I'm basically recovering the same formula for the volume of the parallelepiped. And we're not gonna prove this too much, but you can do the same argument as we did for the 2x2 case, right? So you can convert any general matrix A into a triangular matrix using elementary row operations, which do not change the determinants unless it's plus or minus sign, but if we use absolute value, then it does not change the determinant. So the determinant is unchanged while I'm changing into triangular matrix. And then also, in order to preserve the volume, right, just like we did like a line span of A1 and then added A2, and then here we can just take a span of the vectors forming the base, right? So say A1 and A3 form the base of my parallelepiped. Right, if I take the span of that and then add to that another vector A2, right? I have my parallelepiped that's kind of tilted, right? I can basically do elementary row operations on the columns of my matrix A, which would not change the value of the determinant, but what they will do is that they will convert the kind of slanted parallelepiped into kind of a rectangular parallelepiped, which I can compute the volume of by basically multiplying base height and, well, area of the base times height. Right. So it's conceptually, I think it's okay. Right. So again, like, we can just do basically solve problems using the formula. Right. If I have parallelepipeds defined by three vectors, I can find the volume of it by just putting those vectors as columns in my matrix and computing the determinant and taking the absolute value. All right, so I think and we'll stop here. And add like one last section, linear transformations. We'll do this next time. Any questions, guys? on what we did today? Or anything
No.
else?
No, thank you, Professor.
Yeah, no problem. Yeah, so we'll talk about this next time. So I'm still going through your quizzes 4. So I promise I will finish grading quizzes 4 today. And I'll post quiz 5 and the homework 5 today. And I think, yeah, the midterm, some of you still haven't done it. So I want to grade all the midterms when everyone has done it. So the midterms are due tonight, I believe. So maybe I'll start working on them tomorrow. So I'll try to get them done. as
Okay,
quickly as
thank you, Professor.
You guys want to know your grades. I'll do my best.
I think I do have a question about you said you were posting the homework for 3-1, 3-2, and 3-3.
Yeah, so for this week 8. Yeah, so for week 8, so we did 3.1 through 3.3, right? So we did the determinants. So yeah, I will post homework on online homework, and then I'll post the quiz today.
All right, fantastic.
We'll have one quiz. And I think you have oh no, I guess it would be quiz 6, right? You had another quiz on the previous week.
Yeah, because we have one due this Sunday, and then the 3 would be due the next following Sunday, I'm
Yeah,
guessing.
yeah, okay, so yeah, this one would be 6. Yeah, so quiz 5 you already have, that will be due, and then quiz 6. Oh,
Mhm.
actually, no, you didn't, I didn't give you a quiz on the last week because it's on the midterm, right? Yeah. Yeah, you didn't have a quiz on material from last week because of the midterm. But yeah, you will have a quiz on material from this week. Yeah,
Okay.
so yeah, so basically your next quiz is material from chapter 3 only.
Okay, thank you, Professor.
Yeah,
Just
no
need some
problem.
practice.
Yeah. All
Have a
right.
great weekend.
Hey, you too. I'll see you guys next time.
Thank you, you as well. Take care.